the speaker. The speaker is Ryan, right?
Zachary.
Oh, Zachary, that's the second one. Zachary Loschinskey. And he's going to give a talk on StateSpaceDynamics.jl. It's a probabilistic state space modeling toolkit. And I'm really excited about that.
Okay. All right. Hello, thank you for the introduction. I'm Zachary. I'm a PhD candidate at Boston University. And we've been developing this package for probabilistic state space modeling in our lab for a little over a year or so now. And we're excited to come here and share what we've done. So I'm sure a lot of you are familiar with state space models just from the conversations I've had with some of you. But in general, state space models are just probabilistic models that are used to describe time series data. They include a wide range of models like hidden Markov models and dynamical systems. But the unifying assumption here is that observations are generated from a hidden or latent process that you don't see. And these models have applications across many different domains, such as economics, robotics, but we're all here to talk about neuroscience, where modern neuroscientific tools have enabled the collection of huge, unprecedented amounts of data that are high dimensional and time series. And state space models are a great way to combine both dimensionality reduction and temporal dynamics into one model. So this is the basic vanilla graph for state space models. For those of you unfamiliar, you have a state variable that typically evolves according to a first-order Markov chain. And at every single time step, those state variables give rise to a set or a single observation. This very simple graphical model allows people to build these really efficient recursive algorithms for doing inference in these types of models. Many of you may be familiar with Kalman filtering and smoothing, and maybe forward-backward for hidden Markov models. I'm seeing lots of nods. That's great. So for example, if you had continuous state variables that evolved linearly and Gaussian emission models, you'd end up with something like a typical dynamical system. Whereas if you plugged in discrete state variables that evolved according to a categorical distribution, and maybe you still had Gaussian emission models, you'd end up with something like a hidden Markov model. Okay? All right. So SSMs have been used historically in neuroscience for many different reasons, but I've just highlighted 4 examples that I find pretty cool, kind of divided roughly into animal behavior and understanding neural dynamics. So within animal behavior, state space models have been used for understanding animal learning and quantifying animal uncertainty during behavioral tasks. They've also been used for classifying animal engagement states, whether an animal is super engaged in a task they're in, whether they're just biased, maybe they don't even care anymore and they're just kind of conked out. That's really important to know when you're doing data analysis, and state space models have enabled us to do that labeling. And also for neurodynamics, some cool examples of state space model applications include identifying fixed points and preparatory areas for motor activity that seem to be setting initial conditions for the dynamical systems that control movement. And also this really interesting example from David Anderson's group that found a continuous line attractor that seems to be modulating aggression behavior in mice. So pretty cool applications, kind of all spread out. This is by no means an inclusive list, but just some cool things. There are some existing Julia packages for doing this type of modeling. Some of you may be familiar with that if you work in the space, such as hidden Markov-models.jl, StateSpaceModels.jl, and then Turing.jl, which also provides some tools for state space modeling. Hidden Markov-models.jl, as the name kind of implies, was built for discrete state space model functionality, whereas in neuroscience, we also are really interested in dynamical systems. So this didn't quite fit the bill for what we wanted to do for our analysis. This state space models package, or StateSpaceModels.jl, does have continuous state space model functionality. However, it's limited to linear Gaussian, kind of classic vanilla dynamical systems models. Whereas in neuroscience, we'll see that it's pretty important to have support for things like Poisson and Bernoulli distributions. And Turing.jl provides many different sampling methods that you could use in theory for doing state space modeling and inference. However, these sampling methods can be quite slow compared to inference algorithms that recursively kind of take advantage of that graphical structure. So where do we fit in? We have built tailored algorithms for discrete, continuous, and hierarchical state space models with extensions to non-Gaussian emissions. Now I want to highlight here that our goal is to develop these hierarchical state space models and extend the functionality to non-Gaussian emissions. We do have some redundancy here with some of the other packages that we're working diligently to interface with now, like hidden Markov-models.jl. These were solely built as a means for us to get to our real design target. So put simply, our goal is to provide a set of tools to neuroscientists that need state space modeling in Julia, build functionality for non-Gaussian models typically found in neuroscience, such as Poisson and Bernoulli, and then provide functionality for hierarchical state space models like switching dynamical systems, recurrent switching dynamical systems, these type of things. So, put kind of plainly, our current functionality is Gaussian dynamical systems, Poisson dynamical systems, switching dynamical systems, and then also hidden Markov models, and even these generalized linear model HMMs, or switching regression models. So I'll just jump into a couple examples. The first being a Poisson dynamical system. On the left, you're seeing samples from a Poisson dynamical system we've built using our package. You can imagine you have 10 neurons here on the bottom left of your screen, all kind of spiking, and their spiking is dependent on these two continuous latent variables that you see above them. On the right, we initialize a new Poisson dynamical system, and then we use expectation maximization to learn the parameters of that model from the observed data. And then we do inference to see if we can recover the latent states correctly. And look, we do a pretty good job. Reasonable accuracy, depending on how warm of a start you get it, but reasonably good job. And I want to highlight here that the inference method that we have is really what enables us to use non-Gaussian emission models and handle this type of data you would want to in neuroscience. This is a method that's been known for a long time, kind of, I think, in the statistical literature, but was kind of brought to neuroscientists' attention by Liam Paninsky quite some time ago, where instead of using Kalman filtering and smoothing to find posterior state paths and map estimates, we actually directly optimize the complete data log likelihood with respect to the state paths using Newton's method. Now, what's interesting about this, or what's I guess maybe obvious to some of you about this, is that in a linear dynamical system where you have linear dynamics and Gaussian emission models, this likelihood function is quadratic, and Newton's method will converge in a single step. So actually, this is just as fast as the same time complexity as Kalman filter smoother, and it's mathematically equivalent in the linear Gaussian case. However, this is flexible, and it allows us to move to nonlinear emission models and non-Gaussian emission models. In the typical recursive algorithms like extended Kalman filtering or unscented Kalman filtering, you have to construct all of these local approximations to the map estimate. Whereas here, if you have a Poisson model and then you iteratively run Newton's method, you can get the exact map estimate even for non-Gaussian emission models. Once we have this map estimate, we can construct the posterior distribution through a Laplace approximation. Basically, we construct a normal distribution centered at that map estimate with the inverse of this Hessian matrix as the covariance. Now, again, if you have a linear Gaussian model, this will be the exact posterior because the true posterior is a Gaussian distribution. Now, some of you may be wondering, well, look, you have to invert this matrix. What is this going to do? Well, because of the graphical structure of state space models, this is actually a block tridiagonal matrix, giving it a very special structure and allowing us to do all of these things in linear time because you don't have to invert a huge full matrix. You just have these three bands. And people have developed really efficient algorithms for handling that for us. So great. Okay, switching gears a little bit, no pun intended, to the switching dynamical systems part. We've implemented a structured variational inference approach for learning in switching dynamical systems. For those of you unfamiliar, let's say you had a nonlinear system that was switching between, oscillating in some dimensions, then to another, and then kind of going back and forth. You can approximate these dynamics in a piecewise linear way by fitting a switching linear dynamical system, where this is simply the graph of a dynamical system, and you've added this discrete variable kind of under it to control which dynamical system you're generating observation from at any moment in time. There were labels. Okay, I already explained that though. So here's an example of using our package for switching dynamical systems. On the left side, you can see hopefully in the background there's colors that indicate which discrete variable is being used or which dynamical system is active at any moment in time. And in the front, you can see two continuous latent variables that are being generated. And in this particular case, we have a high frequency mode and a low frequency mode that we're switching in between for generating data. But pictured here are only the latent states. And on the right, you can see after doing parameter learning and structured variational inference, we recover kind of the low frequency modes and the high frequency modes fairly well, but there's still some definite room for improvement here on the amplitude side, and we think switching to a different method might help us out. Okay. In the future, like I kind of hinted at earlier, we want to interface more directly with hidden Markov models.jl for our HMM functionality. That's an amazing tool that came out while we were developing StateSpaceDynamics.jl, and we're working to take advantage of that tool. It's amazing. We would also like to implement more hierarchical state space models, like recurrent switching dynamical systems that people have found to be pretty interesting when trying to understand how neural dynamics give rise to computation. And we would like to move towards a variational Laplacian approach for our hierarchical state space models, as we think they'll solve some of the issues we're having with structured variational inference. And we're currently in the JOS review process, so woohoo, that's pretty cool. All right, I'd like to just primarily thank the lab the DPasquale lab who has been developing this project, primarily Ryan Senne, who's unable to be here today, but has really spearheaded this effort and kind of shown me the ropes along the way. And thank you to the Julia community for being so welcoming and helping us out.
Wonderful. Thank you so much. So other questions? Anybody has a question? So actually, so what you call the Newton method looks like the Gauss-Newton method, or there's a difference, or
that may be.
That may be right, because Gauss-Newton method is just the derivative, right? But this is the Gauss-Newton method. Okay.
You're correct. Yeah.
Okay.
Thank you.
Okay. So thank you everybody for coming. This concludes the Neuroscience in Julia mini symposium. We didn't have so many participants, but we had very active participants, so this is also good. And we are just trying to form a community in Julia. So it will get better, and this is just the start. So thank you again for coming, and have a good evening.